Hello guys, welcome to my channel Algorithm Avenue. In our previous videos, we have discussed about different deep learning projects. Now, in this video, we'll be seeing different loss functions in deep learning. Okay, different loss functions in deep learning. So, before diving into this topic, let's understand why these loss functions are important. Okay, so to understand the importance of loss functions, I have taken an example dataset and a sample neural network. Okay, now this dataset contains two inputs. Okay, two input columns means two input features and one output feature. Okay, now our first training example, let's say our first training example is 4 and 2. Okay, now our first training example is 4 and 2. Now this 4 and 2 will move through this neural network. Okay, will move through this neural network by linear transformation. Okay, with this 4 and 2 will move through this neural network by linear transformation. Okay, by linear transformation, and this output y hat is calculated at the output layer. Okay, at the output layer this y hat is calculated, but initially at initial stages of training, these weights and bias parameters are randomly assigned. Okay, in any neural network. Okay, when you're working on any neural network, initially, okay, initially these weights and bias parameters are randomly assigned. Okay, now after this forward propagation, we have predicted output y hat. Okay, we have our predicted output y hat. Now at initial stages of training, the difference between, okay, the difference between y, that is true output, and y hat, the predicted output, there will be a lot of difference between this y and y hat. Okay, there will be a lot of difference between y and y hat. Now when there is a lot of difference between this y and y hat, you can say that your model is performing really poor. Okay, your model is performing really poor. Now to improve this model, you have to know how much error your model has made. Okay, to improve it, initially the true output, okay, difference between the true output and predicted output is really high. Okay, it is really high. Now means this means that your model is performing really poor. Now what you have to do is, your aim is to improve the performance of the model. Okay, your aim is to improve the performance of the model. Now how can you improve the performance of the model? If you know how much your model has made the error, then you can improve the model performance. Okay, you can improve the model performance. So to measure the amount of error made by the model, we introduce a concept called loss functions. Okay, so to to calculate the amount of error made by the model, we introduce a concept called loss functions. Okay, loss functions. Okay, now what happens is, we calculate the magnitude of error made by this model. Okay, made by this model, by when first training example passes through the model. Okay, when first training example passes through the model, we calculate the amount of error made by the model. Okay, after calculating this error, your model understands that the difference between the true output and predicted output is high. Okay, the difference between the true output and predicted output is high. After your model understands that there is a lot of difference between the true and predicted output, what happens is, it backtracks. Okay, it backtracks, and it has only option to update the weights and bias parameters. Okay, the only option it has is to update the weights and bias parameters. Now what it does is, to with the help of gradient descent algorithm, this weights and bias parameters are updated. Okay, this weights and bias parameters are updated. Now after the updation of this weights and bias parameters, again what happens is, next training example. Okay, next training example is passed through the neural network, let's say 8 and 4. Okay, this next training example is passed through the neural network, and linear transformation on this input data occurs with the help of these updated weights and bias parameters. Okay, updated weights and bias parameters. Again this y hat is calculated, and again this y hat is calculated, and again error is measured, and again you backtrack, and again you update the parameters. In this way this process continues. Okay, this process continues until and fixed weights and bias parameters occurs. Okay, until and fixed weights and bias parameters occurs. When do we get fixed weights and bias parameters? When this loss, okay, this loss is minimum. Okay, when this loss is minimum, we'll be getting fixed weights and bias parameters. Okay, this is the whole intuition on why these loss functions are important. In the next section of the video, we'll be seeing different loss functions in deep learning. In our previous section of the video, we have seen the importance of the loss functions. Okay, in this section of the video, we'll be seeing some loss functions in deep learning. Okay, now these are the loss functions that are available in deep learning based on the task. Okay, based on the task you perform, these are the different loss functions available in deep learning. Okay, when you work on regression, okay, when you work on, let's say, linear regression, okay, you will be having these kind of loss functions, that is MSE loss, that is mean square error loss, and mean absolute error loss, and Huber loss. Okay, now when you're working on classification tasks, okay, when you're working on classification kind of tasks, you need to use these kind of loss functions. Okay, binary cross entropy loss, categorical cross entropy loss, and hinge loss. Okay, when you're working on unsupervised machine learning problems, okay, unsupervised machine learning problems, let's say autoencoders or GANs. In autoencoders we need to use scale divergence loss, and in GANs we need to use discriminator loss and min or min max GAN loss. Okay, now when it comes to word embeddings, okay, when it comes to word embeddings, we need to use triplet loss. Okay, when it comes to word embeddings, okay, word embeddings, we need to use triplet loss. And when it comes to object detection, in computer vision we have object detection. When it comes to object detection, we need to use focal loss. Okay, now in regression we'll be using this set of loss, in classification we'll be using this set of loss, and in autoencoders we'll be using this set of loss, in GANs we'll be using this set of loss, and word embeddings, okay, word embeddings will be using this triplet loss, and when it comes to object detection we'll be using this loss. Okay, now in this video we'll be discussing this five loss functions. Okay, these five loss functions, in this video we'll be discussing, mainly focusing on mean squared error loss, mean absolute error loss, Huber loss, binary cross entropy loss, and categorical cross entropy loss. And rest of the loss functions are not much important, because we will be working in the will be working regarding this loss functions in future. So currently based on the tasks we are working, only only these five loss functions are important. In our previous section of the video, we have seen the different loss functions. Okay, as I said already, I'll be discussing five loss functions, and one of them is mean squared error loss function, that is MSC loss or squared loss or L2 loss. It is also known as squared loss or L2 loss. It is mainly used in the case of linear regression problem statements. Okay, it is used in mainly in the case of linear regression problem statements. Now let's see the formula of mean squared error loss function. That is, loss function tends to yi minus yi hat whole square. Okay, yi minus yi hat whole square, that is true output minus predicted output whole square. Okay, true output minus predicted output whole square. Now what this I represents is, okay, I represents is the row number, that is the first training example. Okay, I represents when I is equal to 1, it determines that it is first training example, and when I is equal to 2, it determines that it is second training example. Okay, now let's understand this with an example. Okay, now this is our example dataset, that is x1, x2, and this is the yi, and this is yi hat. Okay, this is the true output and this is the predicted output. Now this is 4 inputs are our 4 and 6, and our outputs are, let's say it is 10. Okay, it is 10, and our predicted output is 8. And for the second training example, the inputs are 3, 7, and the output is 9, and our predicted output is 10. Okay, this is the example dataset that we have taken. Now what happens is, this first training data goes into our model. Okay, this first training data goes into our model, and this yi hat is calculated, and this is our true output. Okay, now we need to calculate this loss. Okay, we need to calculate the loss for this first training example. We need to calculate the loss for the first training example. So our formula becomes y1 minus y1 hat whole square. Okay, y1 minus y1 hat whole square. Now what will be the loss for this loss function? Okay, for this data, sorry, 10 minus 8 whole square, that is 4. Okay, for this first training example, our total loss function output is 4. Okay, now similarly, when second training example goes into our data, okay, sorry, second training example goes into our neural network, what happens is our formula will modify to y2 minus y2 hat whole square. Okay, y2 minus y2 hat whole square. In this way, I represents the training example number or row number. Okay, I represents this training example number or row number. Okay, now beside this, I have also written the loss function formula as 1 by 2 by a minus y hat whole square. Why this 1 by 2 is written is generally in gradient based algorithms like gradient descent. Okay, in gradient based algorithms like gradient descent algorithm, what happens is what happens is you do the differentiation of the loss function. Okay, you do the differentiation of the loss function. Okay, when you differentiate this loss function, what happens is it will become 2 into ya minus ya hat. Okay, y hat whole square. Okay, y 2 into ya minus y hat. Okay, the general differentiation of x square, what is the general differentiation of x square? It is 2x. Okay, the general differentiation of x square is 2x, so it is 2 into ya minus ya hat whole square. Okay, sorry, 2 into ya minus ya hat. Now, sorry, now this 2, sorry, this sorry for the interruption. Now this 2, this extra term 2 will interrupt the gradient calculation. This extra term 2 will interrupt the gradient calculation. Okay, so to prevent this we add 1 by 2. Okay, to prevent this we add 1 by 2 in the theoretical calculations. Okay, generally this formula is used in terms of theoretical calculations, and this formula is practically used in PyTorch, TensorFlow or Keras libraries. Okay, this formula is used in PyTorch, TensorFlow or Keras libraries. Okay, Keras frameworks, and this formula is used in theoretical calculation purposes. Okay, this formula is used in the theoretical calculation purposes, and this 1 by 2 is added for the efficient work of gradient descent algorithm. Okay, gradient descent algorithm, as this 2 gets cancelled off, only this part remains. Okay, that is why we add to 1 by 2 we add 1 by 2 in front of the mean squared error loss function. Okay, now let's see the cost function. Okay, generally people say that the loss function is similar to cost function. Okay, but loss function is entirely different from the cost function. Okay, loss function is calculated for a single training example. Okay, for individual training examples, but cost function is determined for the overall training example. Okay, sorry, overall data. Okay, cost function is determined for the overall data, and loss function is determined for the single training example. Okay, now let's understand with a small intuition. Okay, now when you pass this data, you got the predicted output as 8, and this 10 is your true output. Now when this loss is calculated, okay, when you send it to the loss function to calculate the loss, what happens is 10 minus 8. Okay, true output minus predicted output whole square, it becomes 4. Okay, now similarly when you send this after completion of this, okay, after completion of this, you send this second training example to your loss function. Okay, now loss will be calculated as, okay, 9 minus 10 is minus 1, minus 1 whole square is 1. Okay, this is the loss function is calculated for individual training examples. Now second comes the cost function. Okay, now how the cost function is calculated is, it is calculated for the overall data. Okay, it is calculated for a batch. Okay, for a batch of data or overall data. Okay, cost function is calculated for a batch of data or overall data. Okay, now for this data, the cost function is sum of the loss function. Okay, that is 4 plus 1 is equal to 5. Okay, this is the cost function output. Okay, this is the cost function output, and these are the loss functions output. Sum of the loss of the batch of data or the overall data is the cost function. Okay, that formula is represented over here. 1 by n summation of I is equal to 1 to n by I minus y hat whole square. Okay, n represents the number of training samples. Okay, n represents the number of training samples that you are considering for your cost function. Okay, now for our data 1 by 2, okay, n is equal to 2, that is 1 by 2 summation of I is equal to 1 to 2 and yi minus y hat whole square. Okay, this is the overall cost function. Now let's see why this extra square term is added in mean squared error loss function. Okay, now the main benefit of this square term in this mean squared error loss function is, let's say we have, let's say first let's remove this square term. Okay, suppose we don't have square term in our mean squared error loss function. Okay, then the loss function output will be 2 and the output will be minus 1. Okay, the output will be minus 1. Okay, now this is 2, loss function output for the first training example is 2 and the second training example is minus 1. Okay, it is minus 1. Now the cost function output will be, oh, sum of the loss function, right? 2 plus of minus 1 is equal to 1. Okay, this is the cost function output. Okay, this is the cost function output. But actually you see that for this training example the loss is being eliminated in calculation of the cost function. Okay, now in calculation of the cost function you're considering this training data, but you are unknowingly avoiding this data. Okay, you are unknowingly avoiding this training data. Okay, this will reduce the performance of the model. Okay, this will reduce the performance of the model. Okay, now your model will only think that the error is 1, but actually error is 2, right? But actually error is 2, but your model is assuming that error has 1. Okay, so to avoid this and improve the performance of the model, you add the square term over here. Oh, sorry, you square the output of the loss function. Okay, you square the output of the loss function. Now another benefit, okay, this is the first benefit of the squaring of loss function, and the second benefit of squaring of the loss function is when you square the loss. Okay, when you square the loss, what happens is the loss gets maximized, right? The loss gets maximized. Let's say the loss calculated is, let's say 0.5. Okay, 0.5 is a calculated loss, but when you square this, okay, when you square this, what happens is it will be somewhere around 2.5. Okay, when you square this it becomes 2.5. Now anything when you zoom it or magnify it, you will get a clearer picture, right? Okay, you will get a clearer picture. So when you square this small term, when you square this small numerical value, it becomes a larger value. Okay, it becomes a larger value, and your model understands. Okay, your model understands and it can interpret well. Okay, it can interpret well in updation of weights and biases. Okay, now what generally happens is when loss function is higher, okay, loss function output is higher, there will be a drastic update on there will be a drastic update in weights and biases. Okay, then okay, and on the other hand, when the loss function output is low, there will be a minimal update. Okay, minimal update in the weights and bias values. Okay, when the loss function output is larger, there will be a drastic update in the weights and biases. On the other hand, when the loss function output is lower, there will be a minimum update. Okay, minimal update in the um, weights and bias values. Okay, this is the second advantage in the mean squared error loss function. And now the third effect of this squaring is, the third effect of this squaring of loss function is, now let's say this is your data. Let's say this is your data. This is your data and this is your binary classifier line. Okay, this is your data and this is your binary classifier line dividing both these data points. And let's say we have another point over here. Okay, now when you compare this data points when you compare these data points when you compare these data points except this data point, you see that losses will be little minimal. Okay, the losses will be little minimal when compared to this data point. Okay, when compared to this data points when compared to these data points, this produces higher loss, right? This produces higher loss. Now whatever means what our model does is it will try to minimize this error, it will try to penalize this error. Okay, it will try to penalize this error. So in the process of penalizing, what our model does is it moves this binary classifier line towards this data point. Okay, avoiding all these data points, okay, avoiding all these data points, what happens is it moves towards this data point which is producing a larger loss, okay, which is producing a larger loss. Okay, now, okay, now generally what happens is, let's say we have error of 100, okay, we have loss as loss function output as 10. Now when you square this 10 value, okay, when you square this 10, okay, y minus y hat I got 10. Okay, when you square this, it becomes 100. Okay, this becomes 100. Now what your model does, it will try to minimize this error. Okay, it will try to minimize this error. So in the process of minimizing this error, it it uh, it will forget these data points. Okay, it will forget these data points and it will move towards the data point which is producing a larger error. In the process of moving this, it will do misclassifications. Okay, it will do misclassifications. Okay, this is a third effect. Okay, this is a third effect of uh, squaring. This is a third effect of squaring in the mean squared error loss function. Okay, these are the three effects. These are the three effects of squaring in mean squared error loss function. First is the cost function, the effect on cost function, and second is maximizing, okay, magnifying the loss. third is third is you are giving much importance to the data points which are producing the higher loss. Okay, these are the impacts of square in mean squared error loss function. Now let's see the advantages and disadvantages by the mean squared error loss function. Now let's see the advantages and disadvantages of mean squared error loss function. First, let's see the advantages. The first advantage of this mean squared error loss function is it is easy to interpret. Sorry, it is easy to interpret. When compared to other loss functions, it is very much simple. Okay, it is very much simple when compared to other loss functions, that is ya minus ya hat whole square. Okay, how it is looking very much simple, right? It is looking very much simple. That is why we say that it is easy to interpret. Second advantage of this loss function is it is easy to differentiable. Okay, it is easy to differentiate. Generally in gradient based algorithms like gradient descent, we uh, we differentiate this loss function. Okay, we differentiate this loss function. Okay, now it is in the form of x square, right? Okay, it is in the form of x square, and the output of this differential is this 2x. Okay, it is 2x. So it is easy to differentiate in the it is easy to differentiate in the gradient based algorithms like gradient descent. Easy to differentiate. Okay, it is easy to differentiate. The third advantage is it has only one global minima. When you plot the graph, of this loss function, okay, when you plot the graph of this loss function, it is generally like this. It is in parabola. Okay, it is in parabola. Now what your gradient descent algorithm does is, okay, it always tries to reach this global minima. Okay, it will always try to reach this global minima. Okay, now what your gradient descent algorithm does is it always try to reach this global minimum point. Okay, it always tries to reach this global minimum point. As it has only one global minimum point, your gradient descent algorithm will not confuse. Okay, it will not confuse as it has only one global minima. Okay, generally in other loss functions, the loss function graph will be in this way. Okay, the loss function graph will be in this way. Okay, now your gradient descent algorithm will start like this and it will slowly go down over here. Okay, it will think that it has reached the global minima, but it has another global minima. Okay, it will forget that it has another global minima point. Okay, this is the main advantage of using this mean squared error loss, as it has only one global minima point. One global minimum. Now let's see the disadvantages of this loss function. Okay, now to understand this first disadvantage, let us assume a data set where weight weight of first person and weight of the second person, and this is the, okay, let me rub this. this is a y predicted sorry, true output, and this is a y hat predicted output. Okay, this is a weight of first person, this is a weight of second person. Y is the, let's say, y is something predicted output that is in kgs or grams, and y hat is a predicted okay, y is a true output and y hat is a predicted output. Okay, now let's say the first person weight is in kgs and second person weight is in uh, 2 kgs. And okay, this is the first person weight and this is the second person weight. For this is the first training example and it's the second training example. Let's say the second person, okay, the first person weight is 2 grams. Sorry, it will not be generally in grams. Let's say it is 6000 grams. Okay, it is generally 6000 grams, and the second person weight is, let's say, 5000 grams. Okay, when you calculate this loss between this two. Okay, let's say the predicted output is some around 3 kgs and the predicted output of this is some, let's say, 7000. Okay, 7000 grams. Okay, 7000 grams. Okay, this is the true output of this lib, okay, of this input features. Now let's take the predicted output. Okay, now let's take the predicted output. Let's say it is in kgs and it is in 6000 grams. Okay, now you see that our first training example is in kgs and second training example is in the form of grams. Okay, now what happens is when you have different units, in your data. Now let us consider for the first training example. Let's say 3 kgs minus 5 kgs whole square. Okay, this is the loss function. This is the loss function for your first training example. This is the loss function for your first training example. It tends to be 2 kgs. Okay, sorry, it tends to be 4 kgs whole square. It tends to be 4 kgs whole square. Okay, it tends to be 4 kgs whole square. But you need to determine the exact numerical value. You need to determine the exact numerical value. This kg square will not be a perfect numerical value. Okay, this kg square will not be a perfect numerical value. So you need to have a common unit. Okay, you need to have a common unit for the entire data set while working with mean squared error loss function. Okay, this is the first disadvantage. And second disadvantage is it is not robust to outliers. Okay, it is not robust to outliers. Let's say this is our data and this is our let's say this is our binary classifier line and this is another set of data. Okay, and we have data point over here. Okay, we have data point over here. Now what happens is as we know that our model generally focuses on reducing the error. Okay, our model generally focuses on reducing the error. Means if it identifies, okay, if it identifies the huge error, okay, if it identifies a huge error, it will much tend towards it will much tend towards this data point to reduce the error of this data point. Okay, so our binary classifier line will be this. Okay, our binary class, okay, our model is avoiding the other data points, focusing just only on this data point. Okay, our model is avoiding other data points, just focusing on this data point. Means it tends that, okay, it identifies that it is not robust to outliers. It is identified that it is not robust to outliers. Okay, these are the two disadvantages of this mean squared error loss function. Okay, these are the two disadvantages of this mean squared error loss function. Okay, one thing I forgot to tell you that while using this mean squared error loss function, the activation function in the output layer, must be linear activation function. Let's say this is a neural network. Okay, this is the output layer. Okay, this is the output layer. Okay, these are the inputs, this is the hidden layer, and this is the output layer. Okay, let's say this is our output layer. We have two nodes in the output layer. The activation function of these two nodes must be linear activation function. The activation function of these two nodes must be linear activation function. It is the condition for the implementation of this mean squared error loss function. Okay, in the next section of the video, let's see mean absolute error loss function. In the previous section of the video, we have discussed about mean squared error or L2 loss. Now, in this section of the video, we will be discussing about mean absolute error or L1 loss. Okay, it is called mean absolute because here in calculation of loss, modulus operation is involved. Okay, modulus operation is involved, so we call it as mean absolute error or L1 loss. Okay, Now the formula for this loss function is equal to modulus of true output minus predicted output. Okay, modulus of true output minus predicted output. Loss function is calculated for the single training sample. Okay, single training sample. And cost function is equal to 1 by n 1 by n determines the number of samples, is and summation of I is equal to 1 to n, modulus of true output minus predicted output. Okay, now why we apply modulus operation is, in previous section of the video we have applied squared operations, we have done the squaring in MSc loss. And similarly in this MAE loss function, we apply modulus operation for the better determination of cost function. Okay, for the correct exact determination of cost function. Okay, this is the total MAE loss, and we'll be seeing the advantages and disadvantages of this MAE loss. Okay, first comes is advantages. Okay, advantages. The first advantage is it is easy to interpret. Okay, it is easy to interpret. Okay, you see that in calculation of loss function, what we have done, just we apply modulus operation between the true output and predicted output, right? Just we have applied modulus operation between the true output and predicted output. Okay, so in this way it is easier to interpret, means we can understand just by seeing. It is not complex, right? Equation is not complex, it is just simpler to understand. So the first advantage is it is easy to interpret. Easy to interpret. And the second advantage is the main disadvantage that we have faced in the MSc losses, the units. Okay, when units are involved in the loss, when units are involved in the calculation of loss, let's say we have taken weights. If suppose the loss, okay, the loss calculated is 1000 kg. Okay, 1000 kg we used to square, that is 1000 kg ka whole square. Okay, 1000 kg whole square, 1000 kg, okay, square. Okay, we even used to square this quantity, and we entirely need to determine the square value also for the units. Okay, we need to calculate the square value even for the units. Okay, so in this loss function we don't have that problem. Okay, in this loss function we don't have that problem. Okay, the second advantage is we need not square the units of the, okay, units of the any feature, any loss function. Okay, any loss function. Okay, the third advantage is it is robust to outliers. In MSc loss, what we used to do is we used to square the loss. Okay, we used to square the loss so that we can magnify. Okay, we can magnify the loss. Okay, we can magnify the loss and better update the weights and bias value. Okay, but when outliers are involved, in our data, when outliers are, let's say this is our data, and this is the outlier. Okay, this is the outlier in our data. Now when loss is calculated between this outlier, let's say it is 10. Okay, it is 10. But in MSc loss we used to square that loss. Okay, we used to square that loss, means which tends to be 100. Okay, which tends to be 100. Okay, which tends to be 100. Now what our model does, it always try to reduce this loss. Okay, it always try to reduce the loss among the data points. Okay, among this data points and this binary classifier line. Okay, now what it does is it will draw a best fit line in this way. Okay, it will draw a binary classifier line in this way, so that it can maximum reduce the loss among the data points and binary classifier line. Okay, now when it draw the line in this way, you see that when it drawn the line in this way, you see that this data point is the loss of this data point is minimizing, but these data points for these data points the loss is increasing. Okay, the loss is increasing and the classification is not done properly. So it is affecting the entire model. But in this case, in MAE loss we don't have that problem. Okay, we don't have that problem because we are not squaring the quantity. Okay, we are not squaring the loss function. Okay, we are not squaring the loss. Okay, we are not squaring the loss. How much the model has calculated, that is how much the loss function has calculated. Let's say it has calculated 10. Okay, as it is it will be 10. Okay, as it is it will be 10. We need not apply any squaring or cubing operation. How much is calculated, that much is left over there, and the model will try to penalize the loss. Okay, we will try to penalize the loss as much as possible. Okay, this is the third advantage of this MAE loss. Now let's see disadvantage advantage. Okay, now the first and main disadvantage is, now we have seen in MSc loss the curve was parabola. Okay, loss function curve was parabola. When that was parabola, what happens is, okay, parabola is nothing but continuous, right? Parabola is nothing but continuous. What happens is, when calculating the gradient descent, okay, in times of calculation of gradient descent algorithm, so the curve, okay, the loss, okay, the gradient descent algorithm main aim is to reach the global minima. Okay, the gradient descent algorithm main aim is to reach the global minima. So when this calculation of this gradients, okay, times of calculation of this gradient, differentiation is involved. Okay, differentiation operation is involved. Differentiation is always suitable and is done on continuous, okay, continuous data, always done on continuous data or continuous graphs. But this MAE loss graph is discontinuous. MAE loss graph is discontinuous. Okay, MAE loss graph is discontinuous, as the modulus operation graph is in this way. MAE loss graph also will be in this way. Okay, MAE loss function graph also will be in this way. So at this time, what happens is, when the graph is in this way, no gradient calculation is done. So that what happens is, the model parameters will not be updated properly. Okay, model parameters will not be updated by the gradient descent algorithm. So that we need to switch to another methods. Okay, we need to switch to another methods like subgradients and another methods. We need to switch to another methods for the calculation of this, to reach this global minima. Okay, to reach this global minima, we need to use some alternative ways. Okay, we need to use some alternative ways. Okay, this is the main disadvantage of this MAE loss function. And there is another disadvantage with this MAE loss function is, in generally in PyTorch or any framework like TensorFlow, the application, okay, for this application of this modulus operation is difficult. Okay, application of this modulus operation is difficult, and this is another disadvantage of MAE loss. Okay, the first disadvantage is gradient calculation. We cannot calculate the gradients. And the second disadvantage is, the usage of this modulus operation is difficult in case of frameworks. In our previous sections of the video, we have discussed about the different loss functions that are used to efficiently work on the regression tasks. Okay, now in this section of the video, we'll be discussing about the final loss function which can efficiently work on the regression tasks. Okay, this loss function is mainly introduced to encounter the disadvantages that are there in the MSc loss and MAE loss. Okay, now this Huber loss, when to use this Huber loss is, when you have more number of outliers. Okay, when you have more number of outliers in your data, then you need to proceed with Huber loss. Okay, now the loss function is L is equal to that is loss function is equal to 1 by 2 yi minus yi hat ka whole square. Okay, 1 by 2 yi minus yi hat whole square. For for when it is used as this when it is used as this MSc loss. Okay, when it is used as MSc loss, when this condition is satisfied, it is used as MSc loss. Okay, what is this condition? By a, that is true output minus predicted output, modulus of true output minus predicted output is less than or equal to this delta. Okay, this delta, the delta value is hyperparameter. You yourself need to set this delta value. Okay, if this condition is false, it behaves as an MAE loss. Okay, when this condition is false, it behaves as an MAE loss. When the condition is true, it behaves as an MSc loss. When the condition is false, it behaves as an MAE loss. Okay, what this condition specifies is, okay, when the data points, okay, when the data points are not outliers, then we need to proceed with this MSE loss. Okay, when the data points are not outliers, we need to proceed with this MSE loss. Okay, when the data points become outliers, the loss function, definitely this value will be greater than this value, right? Okay, when the data points are outliers, this condition will definitely become false. Then we need to go with ME loss, which efficiently handles outliers. Okay, it is this Huber loss is combination of two loss functions, that is MSE loss and MAE loss. Okay, so that the disadvantages in both these loss functions are encountered. Okay, how this loss function looks like is, when this is your MSE loss and this is your MAE loss, in middle, okay, in middle we'll be having Huber loss. Okay, in middle we'll be having Huber loss. When this is your MSE loss, this is your MAE loss, it will be at the middle of this MSE and MAE, means it will not be either that side or not be either this side. Okay, it will be in the middle of the, okay, it will be in the middle of this data points. Okay, it will be in the middle of this data points. Okay, this is the entire Huber loss. Okay, this is the entire Huber loss, which is a combination of MSE and MAE loss. Okay, in this section, okay, in this part of the video, we have discussed three loss functions, that is MSE loss, MAE loss and Huber loss, which are used for the regression task. In the next part of the video, we'll be discussing about the binary cross entropy and cross entropy loss functions, which are used for the classification task. Okay, hope you like this video. If you like the video, please like, share and subscribe. Thank you.